So in this video, we're going to figure out how to solve circuits in a much more quicker, much more efficient way than we have by writing lots of equations and lots of unknowns. And the way to see how that could be is by asking a rather interesting question. What does the source see? And of course, voltage sources and current sources don't have eyes, but I'll show you what that means. When you go down the path of asking what the source sees, that leads to the concept of equivalent circuits, one of the most powerful concepts in circuit theory. And we'll explore series and parallel combinations and learn how to think about circuits in terms of these structural components. Let's go back to our example that we did last time. We have a series combination of resistors and a voltage source. And what we calculated last time was the output voltage was proportional to the input voltage with the constant proportionality. That's the resistor R2 divided by R1 plus R2. And this, as I pointed out last time, is called voltage divider. And that applies anytime you have a series combination of resistors and you apply a voltage across them. The voltage across one of them is that resistance divided by the sum of the resistances. That's a rule that you can use to simplify your life. I asked you last time what was the voltage across R1, and I think it's pretty clear, but if you apply a voltage divider, it's the resistance of the resistor I'm talking about divided by the sum times Vn. Very easy to see, and of course by KVL, this and this have to add up to be Vn, so everything checks out. Well, what does the source see? And what do I mean by that? The voltage source in this case certainly knows what its voltage is. The question is, it gets to see through the current. So the idea is I'm going to put the resistors in a box so that the voltage source can't cheat. The only thing it can do is figure out its current, the current going into the box, I1, and based on how that's related to the voltage source, figure out what's inside the box. Well, we know that V out is equal to this, and we want to know the current I1, but KCL says that I1 is equal to I out. That's the way it always works out for a series combination. The current goes straight through them, and so it's easy to see the currents are all the same. Well, I can figure out I out from V out by simply dividing by R2, and that's what I get. So, what does the voltage source see? Put it in a box. For all the world, the relationship between the source voltage and the current that it's supplying to the circuit looks like that of a resistor. A single resistor having a value equal to the sum. And that's the idea of what's called an equivalent circuit. So, what does the source see? It looks in here through its current, and it sees something that behaves just like a single resistor whose value is the sum of the resistances. Of course, it doesn't know if there's a sum. It might see a resistor that looks like 1 kilo ohm. It doesn't know how many resistors, or if there's only one resistor in there. That could equally well be the case. But the equivalent resistance of a series combination is the sum of the resistances. You can really use that to simplify your calculations for circuits. And by the way, this result all comes from the VI relations, KVL, and KCL, putting them in a much more concise, understandable form when we think about equivalent circuits. So, like I said, it's a single resistor. Now, let's try another simple circuit, and this one has what's called a parallel structure. We have three circuit elements in parallel beside each other, connected together with wires. And that's called a parallel circuit. So we have two resistors in parallel, and a current source has been placed in parallel with that. And what I want to do is I want to find out how the output current, the current through R2, is related to the input current. Well, how many nodes, how many loops are there for writing KVL? And you should see that there are two nodes. There's a big node here and a big node down there, but we're only going to write KCL at that node. And there are two loops, so we get exactly the number of equations we need. We have two VI relations, and the third one is for the current source. We have the KCL equation. One KCL equation, we have two KVL equations. One thing to point out is that when you have resistors in parallel, it's pretty clear that the voltage across them, each of them is the same. And since the current source is in parallel with that, all the voltages here, all the voltages are equal to each other. So that's not really a question. The question is, what is this current and how it's related to IN? Well, all we have to do is put it all together. It's not hard to show that this is the result. And the way you do that is by looking at this set of equations here, the VI relations. Because these two voltages are equal, these two quantities are equal, and I can substitute for I1 in this equation by solving this set for I1. What I get is I1 is equal to R2 over R1 times I out. And if I substitute that in there and solve, I will get this result. And this is known as current divider, as you might expect. So in a parallel circuit, if you have a current going in, it splits between the two resistors such that the current through this resistor is the value of the other resistor divided by the sum. And so it works in a similar way to voltage divider, except it's not the resistance of the element you're talking about, it's the other resistor. Okay, so what does this look like? Well, again, because we get that for the input-output relationship, well, the only way the current source can see what's going on is to look at its voltage. Well, that voltage is just that. Well, that's again the VI relationship for a resistor. It looks like a single resistor whose resistance is the product over the sum. And I use this shorthand notation for that result. So R1 parallel R2 means R1 R2 divided by the sum of R1 and R2. So again, what the source sees is a single resistor. It does not know that there are two resistors in there. All it can tell, it looks like one resistor. So the series and parallel combination structures are very important to recognize to help you simplify and see what's going on. So let's go through this little exercise here. I'm not going to tell you what kind of source I'm going to attach out here. It doesn't really matter. The question is, what does the source see? Well, we have to figure out the structure first. It's clear that R1 is in parallel with all of this. Well, what's all of this? I see R2 in parallel with R3 up there, and then that's in series with R4. And that's going to allow us to figure out what the equivalent resistance is. So let's start with the parallel combination here. That looks like a single resistor whose value is R2 parallel R3. This set now looks like a single resistor, whose value is R2 parallel R3 plus R4, because this parallel combination is in series with that. And then this single resistor, which is what that looks like there, is in parallel with R1. And so our final result is, it's a little complicated, but very simple to write. And that is that R1 is in parallel with the combination R2 and R3, which is in series with R4. Well, I want to use those results to solve a circuit the easy way. And this is actually a pretty practical circuit. So what I want to point out here is that this is the system we've already been talking about. Okay? And what usually happens is when you try to pass that signal onto the sink, that it has an input resistance. In some sense, its equivalent resistance is something which we're going to call R sub L, and L means load. And the question is, does the relationship between Vin and Vout change because there's a load resistance out there? And you might say, well, geez, this voltage here is the same as that voltage there, so probably it doesn't change. Well, that's not quite true. That's because these are in parallel, and these voltages are actually across the parallel combination. There's something to figure out there. I've essentially given away how you analyze it. What we discover is that the output voltage is, using our series and parallel combination rules, this looks like a single resistor, which is R2 in parallel with RL, and then that's in series with R1. So we simply use voltage divider to figure it out. And this is the concise expression, and when you simplify everything, you get this for our final answer. Well, that doesn't much look like the result that we had before, which was R2 over R1 plus R2 times Vn. So when is there a situation as we change RL that this result looks like that? If you think about that for a second, there's sort of two extremes to look at. RL going to 0, RL going to infinity. That's the easy cases to look at. It was pretty clear if you had set RL to 0, the output is 0 volts, right? Because there's an RL in the numerator. More interesting is RL going to infinity. When RL goes to infinity, this term down here essentially disappears because these terms are getting big, and then the RLs cancel, and sure enough, you get this result. So, if you want to develop a system such that when you attach it to the sink, it has a input resistance RL, it better be that RL is big. And it's going to take until the succeeding video we define what big in comparison to what is. That's in the next video. All right. So, in summarize the resistor equivalence. So, if you have resistors in series, the equivalent resistance looks like the sum. And voltage divider, what it looks like, the voltage across any one of them is that resistance divided by the sum of all the resistances. If you have a lot of resistors in parallel, the equivalent conductance is the sum of the conductances, and the current through any one of them is that conductance divided by the sum of the conductances. So it turns out writing the current divider rule, which is what this is over here, in terms of conductances makes it look a lot like the voltage divider up here. It's when you write it in terms of resistances, the expressions get complicated. It's a whole lot easier to write it in terms of the conductances in this case. By the way, there's a minor error on this slide. There should be a voltage V here and an I there. That's what we've learned about solving circuits. The equivalent resistance idea comes up because you ask the question, what does the source see? And it turns out, as you can see from all these examples, when you use the idea of an equivalent resistance, along with the ideas of voltage divider and current divider, you can solve circuits rather quickly. And notice we solved that circuit having the load resistor on it without ever writing KVL, KCL, or the VI relations. We just wrote down the answer. That's really very, very nice. So the whole idea about being able to solve circuits easily means seeing the structure, what's in series with what, what's in parallel with what, and finding the equivalent resistances accordingly.